decision support for formulation design. As already announced, we have 2 presentations. I will give you a short introduction into the methods that we used, and afterwards Lukas will show you how it was implemented with BASF. I will just swap my presentation views. Now it should be fine. Now, just a brief word on Fraunhofer. Fraunhofer is one of the largest societies for applied research in the world, actually. Now, what makes us unique is our financial mix. We want and we are aiming at getting half of our budget from corporations with industry, which means that we are striving for innovations. We are a research institute, but we want innovations go live and be of benefit for those who use it. Now, we are a mathematical institute, meaning that there are mathematicians, computer scientists, physicists, and a couple of engineers here in Kaiserslautern. We have been founded in 1995, and it took us 5 years to become Fraunhofer. Now, if you ask why did it take 5 years to become a Fraunhofer Institute, at that time, the Fraunhofer president said, well, mathematics is important, also for engineers, of course, but whether mathematicians can really earn their money, well, let's see. So he let us try for 5 years, and after 5 years he was convinced, yes, even mathematicians can earn their money. So we are Fraunhofer since 2000. We grew, and what actually our mission is to bridge the gap between academic and industrial research and let innovations go live by software. What we develop with our partners, with our customers, are software solutions that solve problems with methods that are not available in the market, that have been developed at our institute. Therefore, our business principles, and I guess this is also the reason why I have the honor to be here. At the end of the day, we are a consulting institute, but consulting not in the sense of McKinsey or others who end up with slides and advices, but consulting in the form that at the end of the day, a piece of software is running with our partners. At our partners, a piece of software with the help of which our partners are able to find better solutions than they found before. So what these pieces of software at the end of the day do is they make complexity handleable. They simplify complexity. Because real-world problems, if you can solve them in an Excel sheet, of course, then it's fine. But if they are too complex, then Excel comes very quickly to its limits. And what we are aiming for is to make complexity intuitive and let the users, so at the end of the day, put you into a position to find solutions that you have not discovered before. This is, I will make it concrete in a minute. This is not tied to one single to one single group of industries, but you see here we are busy in medicine, in production planning, in layout problems, and also in process engineering, chemistry, and this is what we are talking about today. Just a sample of references. This is, by the way, the reason why it is so much fun to work at ITWM. You get to know many, many different industries. You get to know many, many different partners. So today we want to talk about decision support. Why decision support? What is it about? Our notion of decision support is you want to balance costs and benefits. There is not the single best solution in the world that solves your problem. But at the end of the day, you always have to balance cost and benefit. And what you want to achieve is you don't want to pay more than absolutely necessary to achieve the benefit that you are after. What does it mean in the context of formulation and process design? Costs can, of course, be money, euros and dollars. Costs can also be resources, electricity, natural resources, your feedstock. Cost can also be your CO2 footprint, the impact on climate when it comes to scale up. Can also be energy demand. What can be benefits? Benefits can be product quality, robustness, yield, you are after a high yield, and more and others. So think of these different objectives, criteria, KPI, however you want to call them in your context. And the conclusion is that you have many objectives, which means that you have at the end of the day many alternatives that you can choose from. Some alternatives are better for one objective, other alternatives are better for another objectives. And what we are developing are decision support systems that allow you to find the best compromises. Not some compromises, but the best compromises between these objectives. Which one you choose, this is up to the user. But we guarantee that there is no compromise that is better than the ones that we propose. And how we do it, I will show you in a minute. Our playground here is the right-hand side. So we do it by virtualizing, by digitizing the processes, the real world, building the bridge over model simulation to the virtual world, make it as reliable as possible, and then move the way over the bridge again so that the real world problems can be solved in a better way. The mathematical term for all this, what we are talking about today, is multi-criteria optimization. Multi-criteria optimization means, as I already said, you have different criteria here on the left-hand side. And to these different criteria, different variables belong. Degrees of freedom, so things that you can change in order to make the left-hand side better. And of course, constraints. Now imagine the following. Imagine this spider diagram to be interactive. Then we have two solutions here, a blue solution and a yellow solution, which could be a formulation. Each solution can be a formulation. A solution can also be a process to produce actually what comes into this formulation. And then you might say, well, I'm here at this yellow solution and I'm seeing that, in the cost, this is not that good. The deeper inside the green, the better. So I take it here with my mouse and I pull it towards better cost. And I see, great, even I can increase my product quality, but in other objectives, I might lose something. Now, the guarantee that we give to you is there is no solution with the same cost, with the same quality that is better than this one here in these other objectives. This is what multi-criteria optimization is about, and actually what at the end of the day you see from us and what Lucas will show is exactly this: interactive exploration, interactive navigation on your decision horizon. Let us put it first of all in 2 dimensions because this is more easily to draw. Let us take two objectives, cost and deviation from a certain specification that your formulation should fulfill. Ideally, you want to be here in the lower left corner. For 0 cost, the perfect formulation. Of course, this is not possible. You have to pay something. So somehow it is intuitive that there is a border between what is ideally, what you wish ideally, and what is realizable in practice. Typically, you are moving here in this green area, meaning that you increase from point to point, but you are not really sure, can I improve even more towards this ideal point, or did I reach the border? Typically, you stop when timeout is, when your boss comes and says, well, it's finished now, please show me the results. What our philosophy is, don't worry about all this green area. Concentrate on the border. The border is all you need. What you are actually after is you want to see how much do you lose or gain when you move along this border. Look at this point here. I call it the management point. You minimize your cost. Well, you cannot sell it any longer because the deviation from the specification is that large, but it is, you have to guarantee this is the product with smallest cost. Look at this point. I call it the engineer point. You get everything out of your formulation, you get everything out of your plant, but you cannot sell because it's way too expensive. Now, the intriguing point is that there are regions nearly parallel to the axis, regions of nearly zero trade-off, regions of quick wins. You improve here, you improve in the cost significantly without losing much in your deviation from specification. And these regions of quick wins you wouldn't discover without knowing that they are there. And what our algorithms do, they find this border for you, and they find it numerically very efficiently by calculating points only there where the curvature is highest. This is the essence, this is the core of all what we are doing, because calculating can be expensive when it comes to complicated models, either deep machine learning models or physical models that are very complex. You want to avoid numerical computations. And what I want to show to you now, before Lucas will show you how it looks like in application, I want to show you what is behind the scenes. I want to give you a very short glimpse on this mathematical, into this mathematical box, how to calculate points in where the curvature is smallest on a border that actually we don't know. This is the secret of, let's call it secret of adaptive approximation of this Pareto set, Pareto frontier, which is this green line. Now, what are we doing? We calculate, let us stay in 2 dimensions, and I will show to you how it generalizes to higher dimensions afterwards. This has been developed in 2 PhD theses at our institute. And you see it is completely free of context. It doesn't matter whether we are talking about formulations or processes or medical treatment plans. Let us imagine we have 2 objectives. Both have to be minimized, like on the slide before. And we find, first of all, the 2 extreme compromises. The ones that here, the management point, here, the engineer point, the extreme compromises. Now, somewhere between, there must be this Pareto set, which we don't know. But we know it must be inside this sandwich. We have an inner approximation, which is here just the line connecting the points. And we have the outer approximation formed by the tangents to this Pareto set. Somewhere here in between, the Pareto set must be, if it is convex. If not, this is a topic for another day, but let's stay to this today. If this sandwich is too thick, well, we just push the inner hull outside and we get a new Pareto point. And you see that the thickness of these sandwiches, this thickness decreases dramatically fast. And this is the secret of placing the points where the curvature is highest. This method is doing it for you in arbitrary dimensions so that you avoid any unnecessary calculations. Okay, this is behind the scenes. You don't, as a user, you don't have to care. This is just working automatically. Then all these Pareto points, they are calculated somewhere, and let's still stay in 2 dimensions. Now we have them. Still, again, our cost is the deviation from the specification. What to do with them? First thing is, of course, in 2D, we can plot them. But let's think about something. Let's think about a user interface concept that can be generalized to higher dimensions. These are the sliders. And I already, this was this animation. Yes, this is the cheapest point, the management point, which cannot be sold because the deviation from specification is way too high. So I pull it towards the left-hand side and I observe what the trade-off in my cost is. So I directly get the feedback. Is there any region of quick win? And where does the trade-off set in? Here, the length of these green bars gives you a hint. Then, of course, it might happen that, well, you say, no, there is no way that I can sell the product with such a high deviation from my customer specification. Okay, you cannot sell it today, but maybe you can sell it tomorrow. So why not looking into your decision horizon, into your alternatives that are there, and then introducing constraints as soft constraints, as flexible constraints. Today, only these solutions here are interesting. Tomorrow, maybe there are more, maybe there are even less. I don't have to recalculate. I get it, and I can, so to speak, play with these constraints. I can see how much do I lose from these very nice, very cheap solutions when I set a constraint on the deviation from my specification. Now, how does it generalize to higher dimensions? Here it is. Back to our spider diagram. You rotate these sliders. You can put them on such a slider diagram, but you can also have them just vertically, horizontally, one on top of the other. And you see there is no restriction on the dimension. And this is exactly what Lucas will show you in a minute. Now, let me finish with just one other thought, namely comparing different alternatives. Let's think of a process. Think of a process or think of a task that you have to fulfill. Think of something that a separation task that your process has to fulfill, or think of something that your formulation should do, like some coverage of a surface. You have certain requirements and you have a bunch of your formulations. You have 2 or 3 of them. You want to compare them. This is also a typical use case for multi-criteria optimization. Here are different alternatives. In this case, these are process alternatives for a certain separation task. And again, we have here our objectives and we compare these alternatives. And we ask ourselves, which one is the best? Now, in this case, it is easy. The green one is the best. In this case, you want to be here, maximize a certain concentration, minimize the cost. This is your ideal point here in the lower right corner. The green one is the best one. Which is the second best one? Not clear. It can be the red one if you go for if your cost is very important, but it can also be the blue one. The point is, decisions become transparent. This is something that you can show to anyone. You can say, well, if we go for this alternative, if this is important for us, we should go for this alternative. If something other is important for us, let's go for another alternative. But it becomes transparent. You can discuss with sales, you can discuss with marketing, you can discuss with engineers. And this is what we observe very often in our projects, is that people start talking with each other because they start to understand solutions. And this is actually the point with decision support. You see what you can get, but the decision itself is up to you, is up to the user. So with this, I thank you very much for your attention, and I'm happy to hand over to Lucas. Thank you.